Having defined what multiplicative functions are, in this video we're going to study two very interesting functions and see that they are multiplicative. So we have seen that raising the input to a power is a completely multiplicative function, and any function which is completely multiplicative always distributes f of n(m) as f of n times f of m, regardless of whether the inputs are relatively prime, so it certainly works if they are relatively prime. Therefore, a completely multiplicative function is multiplicative. Okay? And we saw some examples of functions that are not multiplicative, and if they're not multiplicative, they're definitely not completely multiplicative. But are there functions which are multiplicative but not completely multiplicative? In other words, is there a point to this other definition? The only examples we've seen are either both multiplicative and completely multiplicative, or neither. Are there functions that are multiplicative but not completely? So there is, in fact, a function that has this property that we've already seen. Tau of n, the function that counts how many positive factors does the number have. This is a multiplicative but not completely multiplicative function. First, we can observe that tau is definitely not completely multiplicative. So tau of 2 is 2 because 2 has two positive factors, 1 and 2. Tau of 4 is 3 because 4 has three positive factors, 1, 2, and 4. But tau of 2 times 2 is not equal to tau of 2 times tau of 2. 3 is not equal to 2 times 2. Therefore, if you input the pair of numbers 2 and 2, which are not relatively prime, tau of 2 times 2 is simply not the same thing as tau of 2 times tau of 2. So this is not a completely multiplicative function. But is it a multiplicative function? So if tau is multiplicative, and it's not constantly 0, which it definitely isn't, then we must have tau of 1 is equal to 1. And that is true, tau of 1 is 1, but that alone does not establish that a function is multiplicative. It's simply a requirement, but it's not enough on its own. So if you check and see tau of 1 is 1, that simply does not prove that it isn't multiplicative. We have not, however, proved that it is multiplicative. So let's set about trying to show that tau is multiplicative. We're actually going to show something slightly different and more general. If we have two positive integers which are relatively prime, then we're going to construct a bijection between two different sets. First, positive factors of the product nm. Second, pairs of factors. The first is a factor of n, and the second is a factor of m. So here's the function that we're going to establish is a bijection between these two sets. If you input a pair of factors, the first is a factor of n and the second is a factor of m, and you output this product, we have to establish a few things. First, this function really does have this domain and this codomain, and second, that it's a bijection. Well, first let's look at, if d1 was a factor of n and d2 is a factor of m, then d1 can be factored out of n like this, d2 can be factored out of m like that. So for nm, I write nm and I factor d1, d2 out, and therefore d1, d2 is a factor of n times m. In other words, if I input pairs of factors, the first of n, the second of m, this really does output a factor of n times m. So I have domain and codomain set up correctly. But why is this function a bijection? Well, we'll establish this. If m and n are relatively prime, then any divisor of mn can uniquely be split up into a d1 and a d2 so that d1 is a factor of n, d2 is a factor of m, and d is the product d1, d2. So this, if we can establish this, it will exactly show that everything here in S1 has a unique pair back in S2 that corresponds to it. This will establish that this map is a bijection. So let's try to figure out why this is true. Why can every divisor of mn be uniquely factored as a divisor of n times a divisor of m? Well, let's suppose d is a positive factor of nm. Define d1 to be this greatest common factor and d2 to be this one. Well, since d1 was a greatest common factor of two numbers, one of which was n, it's certainly a factor of n. And similarly, d2 is certainly a factor of m because it's a greatest common factor of m and something else. Since n and m were relatively prime, the GCD of d and m times the GCD of d and m is simply equal to the GCD of d and nm. Since d is a factor of nm, the GCD of d and nm is d itself. So what we have here is that the GCD of d and m times the GCD of d and m must equal d. But remember, this was defined as d1 and this was defined as d2. So any factor of n times m can be split up as a factor of n times a factor of m, which means it can be done at least one way. It doesn't necessarily show that that's the only way. In other words, we have shown that this function here is surjective. Every factor of nm can be split up in at least one way as a product, a factor of n times a factor of m. We haven't shown that it's injective, that there's only one such way to factor d. So let's try to show that that factoring is unique. So here's our setup. M and n are relatively prime. D is a factor of mn. We want to say that the only way we could have factored this was the way we wanted. So suppose d has been factored as a factor of n times a factor of m, and all values are positive. Continue to denote d1 to be this GCD and d2 to be this one. What we want to show is that d1 must equal x and d2 must equal y. So x is a factor of d because d was simply written as x times y. And x was a factor of n. Therefore, x is a factor of the greatest common factor of d and n, which we defined to be d1. Okay. Similarly, y must be a factor of d2. So our goal was to show x equals d1 and y equals d2, and we've actually made a lot of progress. While I haven't shown x is equal to d1, it's at least a factor of it, and similarly, y is at least a factor of d2. But we also know that x is now less than or equal to d1 and y is less than or equal to d2, because every value up here was positive and a factor of d1 can't be bigger than it. If either of these inequalities were strict, in other words, if x was strictly smaller than d1 or if y was strictly smaller than d2, then xy would be strictly smaller than d1, d2. We already have established that x times y is equal to d. d1 was the GCD of d and n, d2 was the GCD of d and m, and we've already established that that product is d. Therefore, we would have that d is smaller than d, which is definitely false. And this was on the assumption that one of these was actually a strict inequality. So neither of them can be, which means they're both actually equalities. In other words, as soon as I factor d as x times y, a factor of n times a factor of m, I must have that x was equal to this GCD and y was equal to this one. Which means there's only one way to factor a factor of mn as a product, a divisor of n times a divisor of m, which means the map we constructed before is not just surjective, it's actually injective. So there is a bijection between factors of mn and a factor of m, comma, a factor of n. Now let's finish up the proof of showing that the function tau is multiplicative. So wrapping things up, suppose m and n are relatively prime. On the one hand, tau of mn counts the positive factors of the number mn. On the other hand, tau of m times tau of n would first count the factors of m and then the factors of n and simply multiply those two numbers together. Recall, however, the size of a product set is the product of the sizes of the set. Tau of m times tau of n is therefore the size of the product set of ordered pairs, factors of m, comma, factors of n. And we have just shown that that product set has exactly the same size as the set of factors of mn, that there was a bijection between them. Therefore, the number of positive factors of mn is equal to the size of the product set, factors of m, comma, factors of n, which concludes the proof. Tau of mn distributes. It's tau of m times tau of n. So this function tau is in fact multiplicative, but not completely so. In order to state that tau distributes across a product, it's quite necessary to know that the two numbers you're inputting are relatively prime. If they are not, then tau might not distribute so. Well, now we're going to introduce another interesting function called the Möbius function. So a number n is said to be square-free if there is no number 2 or larger whose square is a factor of n. The requirement that m be at least as large as 2 here is quite necessary. If we allowed m equals 1, 1 squared is 1, and 1 is a factor of everything. So a square-free number can't have any square factored out of it, except, of course, for 1. So n equals 1 is square-free essentially by definition. It has no positive factors larger than itself. And any n larger than or equal to 2 is square-free if its prime factorization contains no repeated primes. So then the Mobius function, whose domain is the positive integers and whose codomain is any integer, is given by the following formula. If you plug in n equals 1, you get out 1. So mu of 1 is 1. If you plug in a number that has a square that can be factored out of it, then mu is 0. But if n is square-free, meaning its prime factorization has no repeated primes, then mu of n is negative 1 to the k, where k is how many prime factors the number had. Okay, so this is a little weird compared to many functions you're used to working with, but let's take a look at some examples. So mu of 1 is 1 by definition. You plug in 1, you get out 1. Now mu of 2 is square-free. So since the number is square-free, I count how many prime factors does it have. How many prime factors does 2 have? It has a single prime factor, so I compute negative 1 to the first, and I get negative 1. Similarly, 3 is square-free, and it has 1 prime factor itself. Negative 1 to the first is still negative 1. 4, however, is not square-free. It has a factor that is a square, specifically 4. So if you can factor a square out of the number, the Mobius function spits out a 0. 5 has a single prime factor, and it is square-free, so negative 1 to the first, negative 1. 6 is square-free. It has no factors that are squares. How many prime factors does it have? It has 2 prime factors, specifically 2 and 3. Therefore, mu of 6 is negative 1 squared, which is positive 1. 7 is square-free, and it has 1 prime factor. Negative 1 to the first is minus 1. 8 is not square-free because we can factor 4 out of it, so mu of 8 is 0. 9 is not square-free. I can factor 9 out of it, so mu of 9 is 0. 10 is square-free, and it has 2 prime factors, 2 and 5. So mu of 10 is negative 1 squared is positive 1. 11 is square-free and has a single prime factor, so mu of 11 is negative 1 to the first, or minus 1. 12 is not square-free. You can factor 4 out of it, so mu of 12 is 0. And so forth in this kind of fashion. Why is this function multiplicative? Suppose m and n is not square-free. In other words, I can factor a square out of m. Well, then I can definitely factor a square out of mn. In this case, mu of mn is equal to mu of n times mu of m because the left term is 0. I could factor a square out of it. And at least one of the terms on the right is also 0. Supposing, for example, m has a square that can be factored out of it, then mu of m would be 0, and mn would also have that square factored out of it, and this would be 0 as well. If n has a square that can be factored out of it, you get a 0 here. But either way, you're going to get 0 equals something times 0, which is true. Now let's suppose that both m and n are square-free, meaning their prime factorization is just a list of distinct primes all raised to the first power. Okay? Suppose m has exactly k prime factors, and n has exactly j prime factors. They both have prime factorizations with no repeated primes, so count how many are in the factorization of m, and let's say that's k. Count how many are in the factorization of n, call that j. Since the two numbers are relatively prime, there is no prime number that appears in both factorizations. Therefore, the product is also square-free. I took k distinct prime numbers and multiplied them by j distinct prime numbers, and there's no number shared in between. So altogether, I have k plus j distinct prime numbers in the factorization of m plus n. In which case, since m times n has no square factor and has k plus j distinct prime factors, mu of mn is negative 1 to the k plus j power. But just as in terms of how exponents work, this is negative 1 to the k times negative 1 to the j. but m was square-free with k distinct prime factors, and n was square-free with j distinct prime factors, so we get this equality here. So we now have two examples of functions that are multiplicative, the tau function that counts the number of positive factors, and the Mobius function, which is a sort of way of distinguishing whether a number is square-free or not. But can we easily compute values of these functions? For the Mobius function and for tau, if you want to compute how it acts on a large number, you kind of have to hack through a bunch of unpleasant work and drudgery in order to figure it out. Is there going to be a nice formula? So suppose a function is known to be multiplicative, for example, tau or mu. If we can determine how it outputs on prime powers, we can actually determine how it outputs anything. So for any number 2 or larger, that number has a factorization as a product of prime powers, where the primes are different and therefore relatively prime to one another. So since all of these prime powers are relatively prime to one another, and the function was assumed to be multiplicative, n is written as its prime factorization. Since each of these prime powers is relatively prime to each other and f is multiplicative, f distributes like that. So if you can figure out how f acts on a prime to a power, you can actually, through the fundamental theorem of arithmetic, determine how f acts on any n. But I do want to point out, it's not enough to know how to apply f of a prime. You need to know how to compute f of a prime power. Well, mu and tau are both multiplicative, so we can determine how to compute values of mu and tau if we can determine how to compute values of prime powers. Mu is more straightforward. How does mu act on prime powers? Well, if you have to the first power, you're just taking mu of a prime. Prime numbers are definitely square-free. There's no square number that can be factored out of a prime. And a prime number has a single prime factor, itself. So mu of p to the first is -1 to the first. So if I am raising this prime number to the first power, mu of p to the first is just -1 to the first, or -1. But now suppose you're raising a prime to a power which is 2 or larger. So for example, mu of p squared. Certainly p squared is not square-free. You can factor a square out of it, p squared. But p cubed is also not square-free, because you can factor p squared out of it. P cubed can be written as p squared times p. P to the 10th can be written as p squared times p to the 8th. P to the 11th can be written as p squared times p to the 9th, and so forth. So for any power 2 or larger, you can factor p squared out of p to the k, and therefore mu should be 0 because you have a square factor. So if n is written as a product of prime powers, since mu is multiplicative, we can write mu of n in terms of mu of each of its prime powers. If any one of those powers is 2 or larger, then one of these terms here would be 0, and therefore mu would be 0. If, however, every power is equal to 1, then I just had mu of a product of a bunch of primes, and I know how to compute mu of a product of a bunch of primes. It's -1 to how many primes were in the list, which was k. And that's exactly what we expect, because that's how we were already computing mu to begin with. What about for tau? Well, tau is the function that counts how many positive factors a number has. As it turns out, for prime powers, that's very easy. What are the positive factors of a prime power? For example, p to the 4th. The factors are just going to be 1, p, p squared, p cubed, and p to the 4th. In general, the factors of p to the k are 1, p, p squared, all the way up to p to the k. How many factors are in this list? A lot of people would look at this last term and conclude there's k, except we actually started at p to the 0. And the list starting at 0 and ending at k has k plus 1 terms. So there's k plus 1 distinct positive factors of p to the k. So tau acts on p to the k and spits out k plus 1. That's how many positive factors there are of p to the k. So for any n written in a factorization of prime powers, tau is multiplicative, so I can split up this input in terms of its prime powers. But observe, tau of p1 to the n1, tau of a prime power is just the power plus 1. So tau of p1 to the n1 is n1 plus 1. Tau of p1 to the n2 would be n2 plus 1, all the way until tau of pk to the nk is nk plus 1. So let's take a look at an example. How many positive factors does 25,600 have? What would be really unpleasant is trying to list out all the positive factors manually, but what we can do is we can factor 25,600 pretty easily. It's 256 times 100. 256 is 2 to the 8th, 100 is 10 squared, but we want a prime factorization, so 10 squared is 2 squared times 5 squared, so in fact 25,600 is 2 to the 10th times 5 squared. Since tau is multiplicative, tau of 2 to the 10th times 5 squared is just tau of 2 to the 10th times tau of 5 squared. But we know how tau acts on prime powers. It's the power plus 1. So tau of 2 to the 10th is 10 plus 1, and tau of 5 squared is 2 plus 1. 11 times 3 is 33. There are 33 distinct positive factors of 25,600. Here's a list, but we actually weren't asked to find all of the positive factors. We were simply asked how many are there. So if someone walks up to you and asks, what are the positive factors of 25,600, you have a long problem ahead of you. If someone asks, how many positive factors does it have, all you have to do is what we did above, compute tau of 25,600 and see that it's 33.